We present the Phong surface model, which enables efficient 3D model fitting using lifted optimization. Our guiding example of model fitting is tracking the 28 degrees of freedom of the human hand by fitting to sparse 3D data. Doing that in a head-mounted augmented reality system, such as the HoloLens 2, enables a natural interaction mechanism, unlike anything we use in today's computing systems. On the HoloLens 2, there is a powerful CPU and GPU, but they are reserved for applications, so hand tracking must be completed in just 4 gigaflops on a digital signal processor. That's about 1% of the processing power of an iPhone 7. The key to efficiency in the previous work was the use of a smooth surface model, subdivision surfaces or B-splines. The smooth surfaces allowed the use of a method called lifted optimization, which greatly reduces the number of iterations used in model fitting and allows the use of many fewer data points. Although individual surface evaluations were 7 times more expensive compared to a polygon surface, the overall reduction was a win. But to get real-time in 4 gigaflops, we needed to get that 7x back. To do so, we introduced a new surface model, the Phong surface. It's nearly as cheap to evaluate as a polygon mesh, but preserves the benefits of lifted optimization, that is, fast convergence with fewer data points. The inspiration for the Phong surface comes from the Phong shading technique in computer graphics. The idea is to use the polyhedral surface model, but to interpolate the surface normals. Let's look at this in detail on a 2D example. We take the non-smooth polygon model and interpolate normals as if from the smooth surface. Now let's see what happens when we try to fit the model to some data. We form correspondences as usual from data to model, and as is common, we don't just match the closest point, but we minimize a weighted loss, combining distance to the surface and agreement of the surface normal with the data. Notice the blue arrows. These indicate the contribution of the surface normals to the correspondence updates in lifted optimization. The polygon model does not have these contributions because its surface normals are identical at any position within each face. These updates improve both speed and accuracy. Here we show a comparison of fitting methods for 2 toy examples, a kidney bean and an ellipsoid. We compare 3 types of surfaces, subdivision surface, Phong surface, and triangular mesh, and 2 types of optimizations, lifted optimization on the top row and ICP or iterative closest point on the bottom row. In all cases, lifted Phong converges as fast as lifted subdiv, but has the runtime cost of just triangular mesh. On the harder kidney bean shape, the triangle mesh is not only slower, but the lack of pull from the surface normals means it has more local minima. Taking this back to HoloLens, lifting means we can use just a tiny subset of the data, the green dots shown here, and the Phong surface means we can do so cheaply and reliably. Putting it all together, we have fully articulated tracking, which deals with both hands jointly, running in real time in 4 gigaflops of compute. Our technique applies not just to hand tracking, but to any situation where efficient surface model fitting is required, particularly on low-power devices. Thank you for watching.